Hello everybody. This video is going to be about VSEPR theory. We're going to review the basic procedures for us to determine the electron geometry and molecular geometry of a covalent compound. Here, this slide shows us the guidelines. And the most important thing that we need to know here is you need to know how to draw Lewis structure first. So that's a very important step that you need to do first. Then the second step, we need to count the total number of the electron groups, and then in the next one, we need to count the number of the bonding groups and the number of the lone pairs. Bonding groups means chemical bonds. Then the last step is we can determine the electron geometry and molecular geometry. This is a website I used during my teaching of VSEPR theory. If you don't know this website, I highly recommend you play with it. It's quite clear when you because you can visualize those three-dimensional geometry. You can rotate it, and it will help you. All right, now let's go to the next slide and use the examples to demonstrate how we use VSEPR theory to determine the molecular geometry and electron geometry. This is a table from your textbook. Let's use the examples to demonstrate how we use this table. First example is the BF3. BF3. Like we discussed in previous slides, you need to draw the Lewis structure of this molecule first. So here is the Lewis structure of this molecule. You have three fluorine terminal atoms around the boron center. Boron has only 6 electrons, and if you remember, this is one of the exceptions of the octet rule. Electron deficient boron center. Because fluorine cannot share more than 2 electrons to form double bond, therefore boron will stay as 6 electrons center. All right. Anyway, so this is the Lewis structure of this molecule. Now let's use this table. First column, the number of the electron groups. That's second step. We need to determine the number of the electron groups. Remember, electron groups means lone pairs and chemical bonds. So when you look at the boron center, it has 3 BF single bonds. That means you have 2 options here, 3 electron groups. Now the next step is step 3, determine the number of the bonding groups and the number of the lone pairs around the central atom. Boron center has 3 BF single bonds, and it does not have any lone pairs, so you have 3 bonding groups, 0 lone pairs, so you choose this option. That means electron geometry for BF3 is trigonal planar geometry, and the molecular geometry is also trigonal planar. Bond angle is about 120 degrees. So if you want to label the bond angle, that is about 120 for this molecule. All right, this is the first example. Now let's take a look at the second example. CHCl3. Well, if you draw the Lewis structure of this molecule, first step, then it would be something like this. 3 chlorine terminal atoms and 1 hydrogen atom. Now let's use this table. You have electron groups. You have 4 electron groups around the central carbon atom, so it should be one of those 3 options. Now step 3, determine the number of the bonding groups and number of the lone pairs. 4 bonding groups, 0 lone pairs. That means it's right here. So that's option 1, number 1. That tells us that the electron geometry of this CHCl3 is tetrahedral geometry, and the molecular geometry is also tetrahedral. The bond angle is 109.5. One thing I do want to mention here is, if you remember how we draw the 3-dimensional structure of those geometries in 2-dimensional plane, we use dashed wedge and solid wedge. which means that if you have the hydrogen, carbon, and one of the chlorine in this screen plane, then you would have one chlorine below the screen, and you have one chlorine above the screen. Okay, we use dashed wedge to represent the chlorine that is below the plane, below the screen, and we use solid wedge to represent the position of this chlorine which is above the screen. Okay, so this is second example. Third example, let's see, H2S. If you draw the Lewis structure of this molecule, you will find that you have 2 lone pairs on the sulfur center, okay, and you have 2 hydrogens. Now, let's determine step 2. Let's determine the total number of the electron groups. You have 2 lone pairs and 2 chemical bonds. That means you have 4 electron groups. Again, you have one of the 3 options right here. 2 chemical bonds, 2 lone pairs. That tells us the electron geometry is tetrahedral, but the molecular geometry is bent. Okay, is bent, which means you have an angle between the 2 sulfur hydrogen single bond, and that is less than 109.5 degree. Okay, so this is example 3. Example 4. Okay, let's take a look at this IF3. Again, if you draw the Lewis structure of this molecule, you will find that you have 2 lone pairs on the iodide center. Okay, and 3 fluorine around the iodide center. Okay, now let's count the total number of electron groups. 1, 2, 3, 4, 5. 2 lone pairs, 3 IF single bonds. So 5 electron groups. Now, as you can see, that it has 3 bonding groups and 2 lone pairs. That tells us the electron geometry for this molecule is a trigonal bipyramidal geometry, but the molecular geometry is T-shaped. Okay, it's T-shaped. It's sort of like a, something like this. Okay, but the bonding angle between this 2 IF bonds is not 180 because the 2 lone pairs need more space. It will push this 2 fluorine to your to your right side. So the bonding angle is less than 180 degree. Okay. Right. So this is the 4th example. Now let's see the next one, SBF6 minus. Okay. Now draw the Lewis structure. Okay. This is the Lewis structure. Okay, of SBF6. Oh, I don't like this fluorine. Let me erase this. Okay, to make it better. All right, this is a Lewis structure of SBF6 minus. All right, now if you take a look at the total number of the electron groups around the antimony central atom, now it would be 6. Okay, 6 antimony fluorine bonds. So it's one of the 3 options here. Now you have 6 bonds. Okay, that means 6 bonds, 6 bonding groups, and 0 lone pairs. It tells us the electron geometry is octahedral and the molecular geometry is also octahedral. Okay, the typical bonding angle is you have 90 degree. Okay, here if you get confused about the bonding angle, it's time for you to go to that website I recommended in the previous slides to see where that 90 degree is. Okay, but let's just try the three-dimensional geometry or structure of this polyatomic ion in the two-dimensional plane. You have antimony, and if you have this fluorine, antimony, and this fluorine, the three axial atoms in the same screen plane, then you would have one fluorine, okay, below the screen, this fluorine above the screen, and again for same thing for the other two fluorines, one fluorine below, the last one should be above. Okay, so this is how we draw the three-dimensional structure of the SBF6 minus in two-dimensional plane. Okay, I hope this video can help you refresh your memory about the VSEPR theory, and let me know if you have any questions.